Yo, what's up, everybody? Welcome back. Today, I want to write a float parser. This might end up being really quick, might not. I don't really know. I wasn't really planning on streaming today, but on my way home from my parents, I was like thinking about this a little bit, and I was like, oh shit, stop thinking, no more thinking about this. We gotta figure it out on stream. So, the thought here is we're making a website, right, to like track food intake, right? So like something that I might want to do is I might want to say, hey, I had like 1.5 servings of a thing, right? Which makes me wonder, okay, well, how do we store 1.5 in an SQL database, right? Our SQLite database has, strings. It's got ints, it's got blobs, right? So like it would be pretty straightforward to be like, okay, I'll take like the thing the user entered, parse it as a float 32, store that in the database, great. But then what happens if I go to my website and I type in 1.5, hit enter, and then the thing comes back? Is it still 1.5? Probably not, right? Like not all decimal numbers are representable in 32-bit floats. So like, is that going to turn into something else? Maybe it makes more sense to store it as a string and then like convert it to floats every time we use it. Maybe it makes sense to store them as ratios. I don't really know, right? And so like, I think part of making that decision involves understanding like the cost as well as like the loss of what happens when you do float parsing. Right, so that's what I want to do is I want to write a shitty float parser. I don't want to like look up the answer because it's kind of fun to do the puzzle, and I kind of want to see like what do we come up with, and then we can kind of compare that to like a real answer after. That's what I want to do. That's what I want to do. So let's do that. Let's get moving. So for later, we'll say, I guess we're gonna start with trying to make a float out of nothing. Right? So we have floats support on our CPU. The CPU knows how to interpret some sort of bits as floating point numbers, and there's some like hardware inside to do those, to like do math on those things. I guess the first thing is understanding like what the format of that is. I know that they're like 32 bits, and we've done like a little bit of hand rolling our own float library that does it in integer math before, so we've got like a bit of a feel for it, but we should look it up again. So float format is probably pictures. I like pictures. Yeah, so this, right? So they have 32 bits. You got basically something that's of the form, color, like something of the form 2 to the power of n times n, I think, if I remember correctly. In the same way that you can write like 1000 as 10 to the power of 3 times 1. Or 1001, this can be written as, 10 to the power, or 1.001 times 10 to the power of 3 or something. Yeah, something like this, right? So really this 1 is implicit and this 10 is implicit. So you could store this number as 1 and then probably some like, to store this, plus some exponent, probably. That's probably what's happening in this picture, if I remember correctly. That you have like, mantissa is like the actual relevant data, and then exponent here is like what you're like the power or something. Yeah, we'll see. This could be wrong because I'm not sure if this 1 is actually implicit or not. That's probably not, right? Might be. Might not be. We'll see. I guess because if you had 2000, there's no 1 in there. This is 2 times 10 to the power of 3. So it's probably just most significant bit here with like the remaining stuff, right? So it's probably like if you had 2, 2, 2, 2, you're probably storing all 4 of these, and the decimal goes here times 10 to the 3. So you're probably storing something like that, but in like base 2, probably hand wavy. I'm okay Googling this because this isn't the problem we're trying to solve. So let's look up IEEE float Wikipedia. They'll probably tell us. They will probably tell us. Base, which is either 2 or 10 you can have 10. Okay, we're using base 2 floats, right? P here, what do they have P as? Precision. This is like too fancy. I just want binary 32. Single precision floating point format. This is it. Okay. Okay, here we go. So here they have, this is probably what we want, right? Real no value is assumed by a 32-bit binary 32 with a given sign. Oh, right, yeah, sign here. So this is -1. Negative, because the sign is 0, so 1 if positive, probably. Then they have 31. Is that what this is? What the fuck am I looking at? Oh, exponent minus 127 here. Times 1, so there is an implicit 1 here. Plus the binary number or something, right? That's probably what this is saying. 2 to the negative I from I1 to 23. Where's the 23 coming from in here? The number of bits in the fraction? Yes. Yes. Okay. So can we think about this a little bit simpler? This is probably a fancy way of saying that this is a signed 8-bit number. I think that's what this is saying. We'll check that later. And then this is probably just 1 plus number. Right, I think that this is just a fancy way of saying number. Pretty sure. So let's make a main club function main. So we know that we have like float is a packed struct backed by a U32. And this thing has this goes, I can't remember which way zig packed structs go. Let's double check. Least to most significant. So it's mantissa, which I think they said was 23, then exponent, which was 8, and then sign, which was 1. I think. Does that add up to 32? 23 plus 8, 31, 32. Yeah, that's right. Okay. So let's just start. Let's say like 2F32. You know, this takes self as a float 32 and returns an F32, like the zig internal representation of that thing. And we probably just do like float like bitcast, I think. Yeah, we can probably just do this, right? So here, let's say that we did mantissa 0, exponent 0, exponent equals 0, and this is actually an I8, right? We said this is signed, and sign is 0. So what do we think that this is going to be? This is going to be 1 plus 0 times 2 to the power of 0, maybe negative, right? So we're expecting this to be like 1 or -1, one of the two. So can we do stud debug print a number val, right? And let's see what happens. Zig run main.zig. He's mad because oops, to F32. My bad. Okay, that's 0. That's 0. Okay, what if we put 1 here? I assume this just becomes 1. Oh, interesting. This becomes 1, like a very, very small power of 1 or something. So I guess this is wrong. So maybe exponent is a U8, but kind of offset by 127. Because I think that we also saw that. Like, we saw like a minus 127 in there. Okay, that's close. Mantissa 0 again. Okay, there we go. Okay. that's good. So this is, if the formula is minus 127 on the exponent, then 1 plus 0 times 2 to the 0 is equal to 1, right? That makes sense. So if we put 128 here, then I guess that we're saying that this is 2 to the power of 1, so we expect this to be 2, right? I think that makes sense. Which it is, good. So we keep incrementing this guy and it becomes like 2, 4, 8, 32, right? So like 129 would be 4, right? 129, 130 would be 8. Cool. And then if we do like 126, then this is, divided by 2. So this should be 0.5. Yes. Okay, that makes sense. So then if we do this, we flip the sign bit, then it's negative. Simple. Okay. And then if we do this, this is like 1 point. This is in. Let me think for a second. I think that the mantissa is like 1 plus mantissa divided by 2 to the 23, I think. Right? Because that's how many bits are in this thing. So 1 is like the very smallest thing we could put in there, right? So if we did like 1 shifted left by 22, then this is like the 1 goes like in the most left digit that it can fit in. So at 1.7, this is like 1.5, I think, right? Because this is you're putting a 1 in something base 2, so it can only go like half steps. And so we have 1 plus 1/2, I think. So this should be 1.5, if I understand this correctly. Nice, negative 1.5 because the sign bit is set. But that is right. Which means that if I do to the power, shift this off by 21, then we're gonna get 1.25 because we're like half of a half, I think. Right? Yeah. And then if we do 11, like binary 11 shifted left by 21, this is going to be plus a half plus a quarter, right? So this is going to be 0.75, I think. 1.75. Okay, I think we get it. It's not that crazy, right? So it's what is the actual formula for this? This goes so over my head. Yeah, I'm not explaining it very well, which is not helping. Okay, so let's run it back. So I think that the number is, you have 23 bits in binary to show like 1 point something, right? 1 point something. This is mantissa, right? This is 1 point something times 2 to the power of number, right? We'll say that. So you put a 0 in here, this thing just becomes 1. So you cut that out, right? So we put 127 here because this number is offset by 127, but like this 127 means 0, right? So ignore exponent, which means that we're just working with a mantissa. Now, this guy has 23 bits, right? And they kind of start as like biggest bit here, smallest bit here, right? So if you make this guy 1, you're going to get 1.000000001, except this is not decimal, this is binary, right? So in the same way that if you have like 1.1 in decimal, you're doing like 1 plus a tenth. In binary, 1.1 is 1 plus a half, right? So each digit goes down, like gets cut in half. And so like this is like 2 to the power of negative 23 essentially here. So I think the formula is like 1 plus 2 to the power of negative 23 times mantissa. All of this times 2 to the power of exponent minus 127. I think that's what this is saying. So we could probably encode this exponent in a way where it doesn't look like this, right? Just pretend that this is like n, right? And then so mantissa is kind of like a little bit complicated, but like fine. Okay. Okay. I think I understand this. Now, if we were going to parse this float, what does that mean? Right? So I put in like 0.00001, right? What does this mean? How would we turn that into this representation? I guess we kind of want to figure out, we should probably first start by picking an exponent that makes sense. Right? That probably makes sense. Okay. So here it's really easy to get the exponent in base 10. Probably. Right? We just find the first digit. So it's something like, here, this is 10 to the power of negative 1, 2, 3, 4, 5, right? That's what this is. Because we have to move the decimal 5 places over for that 1 to be it. And then if it was, this would be 10 to the power of 5, right? So I think all we're doing here, is that right? 0, 1, 2, 3, 4. Sorry, to the power 4. Okay, so all we're doing here is looking for zeros, probably. So we're probably counting, this is like, if we see non-zero number before decimal, count digits before dot. This is how you would do this to get power of 10, right? Now, and then if else, count digits after dot before seeing number, right? This gives us power of 10. Now, is there like an equivalent to give us a power of 2 here? Probably. I don't know what it is though. So the thing is like the strings that we're going to be taking in are like inherently base 10, right? Because humans have 10 fingies, and so we think about things in tens. So let's say we guessed the power of 10 right. Guessed is strong. Say we got the power of 10 right. I guess it's probably possible to go from power of 10 to power of 2, right? You have like 10 to the power of A is equal to 2 to the power of B. Surely that's like a thing you can solve for, right? You could do like log base 2 10 to the A is equal to B, right? I think. So this would give us like the exponent if we get the power of 10 right. I don't know how accurate that is. I guess with rounding, it's probably okay. Probably? Is that right? Is that right? Let's see. Wolfram alpha. I think that's right. So if we have like 10 to the power of A is equal to 2 to the power of B, solve for B. I think it's just, yeah, log 2 of 10 to the A. Because log 10 over log 2 is log 2. That's fine. So I think that's fine. So if we were to guess the power, what do we do here? We parse this thing, find the power of 10, convert that into power of 2. That's like one option. The other option here is like, we could just like parse into int somehow and extract power of 2 from there. But I suspect that won't give us what we want. Right? Because like you can represent really, really, really fucking big numbers in floats, bigger than you could represent in an I64, right? I think. Right, because you can input a float as like 1E99 or something, right? That's a thing you can do. So I suspect that this is the right answer. this is at least the answer that I would like to start with. Figure out the power of 10. Convert that into a power of 2. Put that into the exponent. And then figure out the mantissa that, like, makes it work. I think that makes sense. Only if you're willing to give it precision. Maybe, yeah. I mean, it depends on, like, how close this gets. I wouldn't be shocked if, like, this gives us, like, a floating point number that we can use to round to the correct thing. Right? If A becomes... I guess you could just do log 2... Well, I was going to say you could do log 2 of the number here. You could probably get, like, a better approximation if you multiply this by the first number. Right? Probably. Right? If this is, like, 40, you do 4 times 10 to the power of 2. I was gonna... anything more precise than that? Anything more precise than that, then you start just parsing the float again. Which doesn't help us. So let's start there, and maybe we'll see what happens. I guess what you're saying is kind of reasonable too, right? You're saying I'm thinking about it backwards because you only get 23 significant bits, so starting with the 23 significant bits, then finding the power later does make sense, right? So what you're saying that the other option here is that we have like 0.00123456, right, or something. And really, that like the interesting part of this number is the 1234556 with like starting at the biggest number, right? So you could parse this, just keep going forwards along this thing until you run out of bits. There's probably some way to do that, right? So you can probably do something like, you look at the 1, and this is like, this gets parsed as 1 out of 10. Then or I guess this gets parsed as, let me think about this. You can kind of like keep walking forward. 1 is equal to 1. 1, 2 is equal to 12. What the fuck am I doing with my life? What the fuck am I talking about? You need to like convert these into binary as you walk forward somehow. That's what I'm trying to figure out. So I'm trying to think of like some iterative method where you read this 1, you like consume it somehow. Surely that turns into 1. Then you read the 2, so you do times 10 plus 2 times 10 plus 3. Yeah. You just keep timesing by 10 and adding the next number until you run out of bits. And then eventually, if there's too much stuff at the end of this, you just like discard it, probably. Right? At some point, you run out of bits to represent this, and so you just give up. I like that. That seems reasonable. And then figure out the power at the end. I don't know how you get there. Yeah, I still think that you still have to do this like power thing. Otherwise, you have to like, how do you figure out where this thing slots in? Right? Eventually, I have to figure out. Yeah, I think it's fine. I think either way, either order is fine. I think. Let's do that. Let's do this. Let's just do that and then figure out how wrong it is later. That seems reasonable. So we'll say that this was like, figure out what we will do. And then now we're kind of at, figure out power of 2. Let's do that first. I think that that's doable. So given some string, parse float given some string. And this is going to turn into a floating point, right? Probably errorable. And first we're going to like, I guess we'll call this power of 10. Okay. And we're going to be like, I don't know, man. Does an index, does like an iterator here make sense? So we start at 0 and we say like, while si is equal to 0 or something, while I is less than slen and this, I guess it's kind of like this, right? Or a dot. Right? So we're looking for zeros or dots, and then eventually it will be one of those other things. If we don't, we return the thing is 0. So I guess kind of doing that here makes sense. No, we can't do it that way. So if this is this, then return 0. We'll say number is 0. So power is also 0. Simple. Then I guess if let's just validate first because it's easier. If C is less than 0 or C is greater than 9, then return error not a number. Eventually, technically, 1E9 is valid, but we'll tackle that later. Oh, wait. And if C is not equal to a dot, he's allowed to be a dot. And this. Okay. Okay. Sure. So now we know this is a number, which means that now we can just start looking at the number. So I guess really we're trying to track where the dot is and where the first digit is, right? So dot pause equals 0 here, or maybe is equal to null. And we kind of want to, like, while we're iterating, look for the dot. So really this is more like if si is equal to dot, yeah, if I is a dot, we set the dot pause. Else if this is not equal 0, we break. So now, at this point, we have found the first digit, which may be before a dot. Why do I think? Oh, because I is this one in here. Okay, cool. Charbit, thanks for the prime. Congratulations, it's a float. Congratulations. So once we've got here, then we have found a digit. So I guess if we have the dot pause here, then we know that it's like some negative power. Right? So here it's like, here this is some number that's like, you know, some amount of zeros followed by a dot, followed by some more zeros, then a digit, right? So here we know that this is I is this 9. So this is like, this position is like 0, 1, 2, 3, 4, 5, 6. Is that right? Yeah, so I think it's literally just like return negative I minus P, where we are minus the position of the dot. Otherwise, we have to keep parsing until we find a dot. So here we say, you know, keep going till we find a dot. And here I guess we probably set the first digit pause. And then we return first digit I minus first digit pause. That sounds right. Maybe. You can parse my floats anytime. Okay, let's get... Calm down. That seems like it might work. Maybe. Okay, let's do that. Let's say, we're looking for a number that's like, try, what do we call this? Power of 10 of like 1,000, right? So we're expecting this to return 4. Negation of U size, true. So we probably want, so if this is really fucking big, which is possible, right? This number might be like fucking huge. It might be so big that it doesn't even fit in an I8. In which case, what the fuck do we do? I guess it becomes infinite. I assume infinite is just marked by max value or something? So this is gonna be like P, I minus P. And then, we wanna like clamp that shit? I guess? You know, something like this? Like this? And I assume that this will make it infinity. I assume. Could be wrong. And then we return the negative. I guess if it's 128, then we can't negate it. I think that you have more on one side. I can't remember which. So if we'll do it this way, if ret U size is greater than 128, we're greater than or equal to 128, return I don't know, you know, this. I don't remember, but we'll just make it all ones. Otherwise, we can truncate this thing. That seems reasonable. Yeah. Sure. Bitcast on comp time int. Fuck off. Expected integer type found U size? The fuck? Why doesn't it like that? Expected sign integer type found U size. Oh, maybe U7? And then, god damn it. That's annoying. Okay. I don't know. Maybe. Annoying. But we'll make it work. Okay, then we have to do the same thing here, probably. So it's like... And then we'll put a, like, fix me factor out. Whatever. But for now, I guess we should just do that, right? We should do, like, power U size to I8. Okay. So if P is greater than 1.28, I guess we can just go straight to I8 here. No, we can't, because the truncate is... Maybe we can. We'll see. I'm not sure if that works. Power U size to I8, I minus P. Okay. And then here we can do return power to U size I minus first digit pause. And then we actually have to negate this here and not negate it here. There we go. Yeah, that sounds right. That sounds right. Yeah, this truncate doesn't let you do, it doesn't let you do unsigned to signed, I guess. So int cast ret U7 or something. Okay. So here he's mad, probably because in this while loop, we didn't increment I. Okay, so that gave us 4. That's a good sign. 1000 is giving us 10 to the power of 4. That's huge. Let's look at 0.0001, and can we... This should give us negative 1, 2, 3, 4. Huge, baby. Let's go! Power is a 10, baby. Okay. And then if we return the first digit, does that help us at all? I think it does. So can we actually do this? So we're gonna be like first digit and power. Okay? That's gonna return power 10. And this is what's going on here? So this we're gonna have like, I guess it's literally just like minus 0 on SI. Yes. 10 to the 4 is not equal to 1000. Am I just off by 1 here? I might be. 10 to the power of 2 is 100, 3 is 1000. Yeah, you're right, I'm off by 1. I am off by 1. My bad. Good eye. I'm a dumbass. Return this. Okay. So then first digit is going to be S first digit pause minus O. And then I guess we probably have to do this here as well, right? No, because at this point we've found a digit. Okay, we're chilling. We're chilling. I think that's right. Okay, let's look at this again. Return 0, true. This is first digit 0 and power 0. All right. So now we have 1,000 is 1 times 10 to the power of 3, which is now correct. And then 0.0001 is 1 times 10 to the power of negative 4. That's hype. That's hype. And then so if we start throwing in like a, 4 in here, we get 4 times 10 to the power of negative 4, which is hype. Hype, 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 hype. Okay, so now we have a way to like get like an approximate power of 10, right? So we can do something like std math log 2 I guess this is going to be like power of 2 for some string, right? Which I guess can just use this same thing. Power of 10 is actually just kind of like a power type. So here we call power of 10 on the string. And we said that to convert, I guess here this is actually just going to return a U8. Because we don't care about the leading exponent, the first value anymore. That was just to make the power of 2 guess a little better. And I guess an I8 here. So my gut says we do log 2. I wonder if log 2 int rounds down. Is there a log 2 that does not round? No. So we could do this as floats, but my gut says like doing it as ints would be maybe fine. Maybe. So it's like power 10 I guess like we might end up with a number that's not representable, which is kind of interesting. Right, like I guess like if we were to just do the stupid thing here and do power 10 number times 10 to the power of a thing, then like we might end up with a number that's not representable as an I64. So we might have to get like more intelligent about this. We might. So if we do like a log, wow, interesting. Interesting. You could write it as a float, but then you have to do a float parse, which doesn't work, right? So what the fuck are you supposed to do here? Interesting. You could like lookup table this thing somehow, right? Like you could calculate like how would you, oh, we have the graph here. Oh, they're linearly related. Of fucking course. Of course. Which means that this is just a divide? Right, this is just a linear relationship. Hype. So I guess log 10 over log 2 is like some ratio? Must be. Which we can just calculate. log 10 of 10. Am I stupid? Log 10 of 10 is 1. Log 2 of 2 is 1. No? So, like, what the fuck is this? This is literally just. So, we, like. Oh, but log. Oh, it's over log 2. So, is it just the power over log 2? Log 10 2? I think so. Okay, and then if I put like a. What happens when I put if I put like another number in here though, where this 10 to the a is now like times another number? Can you do like log a times 10 to the b? Does this like simplify into something where like the a can come out? Like, can we do like equals 0, solve for a or something? Does that like. This becomes that. That makes sense. Because you like. The log just goes away. That's not helpful. Not helpful. I think you want log AB. Yeah, I like get that to some extent. I understand that like there's a linear relationship to power of 10, 10 and power of 2, right? And it's log base 2, which comes from the idea that like 2 to the power of A is equal to 10 to the power of B, right? If you're trying to solve for A, you log 2 both sides, right? So it becomes A equals log 2 10 to the B, which Wolfram alpha is expressing as log 10 10 to the B over log 2, right? Log 10 2, right? That's what he's expressing this as. Now, what I'm confused about is if I then put like a multiplier in here, C times this, I don't know how this affects it. But I guess we can just do this after. Right? So if you go from like 1,000 to 4,000, like you just have to take your log 2 and add 2 to it in this scenario. That makes sense to me. So let's just start with the ratio, which means that we take you take the power of 10 and divide it by this. No? And then add the log 2 of the multiplier. I think. That sounds kind of right. That sounds kind of right. Yeah, so we'll say there's like a linear relationship between power of 10 and power of 2. First, easier for my brain to parse the first digit after. So we just log 2 the first digit and add that to the output. That feels kind of right to me. So if we do then power of 2, let's just kind of put a little break in here and we'll say Try power of 2 on 4. Right? So this should give us power of 10 is 0 plus log 2 of 4. So this should give us 2. Fuck. Yeah, this thing is failable, true, which means it's the right try. I8 and comp time float. We're gonna completely ignore the fact that float from int exists. We'll ignore that for now. And actually, I want to return this as a float for now, just so that I can kind of interpret this information a little better. Okay, so this gave us 2, so 2 to the power of 2 is 4, that's hype. So now if we put in 8, this should give us 4, or 3, I mean. Nice, so 2 to the power of 3 is 8, that's good. Now, what happens if we put in 10? 3.3. Okay. We should check this, right? So we should, let's like put the numbers in here and like do some sort of like there and back again. I think that makes sense. Samples 4, 10, 100. Let's just kind of see what happens here. And we can go like, it's actually like this in this language. 4 samples. We log something. So we log the thing that we're trying. And then we log the power. And then back again. So power is power of 2 on the sample. And then number is pow 2 to the power. And does this give us the right answer? Right, does this do like a little there and back again? I think this has to be typed. We should new line here. True. Okay. So you get 4, 2, 4, 10, 3, 2. I mean, that's a really good sign. That seems like it's working, right? So we have 10 is 2 to the power of 3.321928. We do that thing back, we get 10. We get 100 is 2 to the power of 6.643856. We get 100 back, basically. Which is pretty sick. Right? So can we put in like, I don't know, 9, 4, 5, 1, 2, 3 or something, right? Let's just see what that does. So this guy gave us not the right number, but it is kind of close, right? Which makes sense because we're only looking at the first digit, right? So since we've lost this 5, 1, 2, 3, we're like losing the second precision. So I think that's kind of right? We're getting 9,000 back, which is what we calculated. Whether or not that's right and reasonable, who fucking knows, right? But seems okay. Seems okay to me. So now that we have an approximate power of 2 that works, at some point we did figure out power of 2, we should be able to like construct some float out of this thing. Figure out float, right? So I guess it's actually figure out mantissa now. So we find the sequence of digits that matter, right? So I think that if you have like, something like this, you want to keep most significant bits. So I think minor 1 over log b a equals log a b if you want to turn that divide into a multiply. So here we're dividing by, dude, my brain. So we have log 2 plus this over that. So you're saying that I can convert this into a multiplication because I can invert the 2 and the 10. So you're saying I can do times log 2 10 and get the same thing. And I guess because floating point multiplication is faster than division is your argument, which I think is true, right? I think that one of them is faster than the other. Sure. Still works, which is good. Okay, so if we parse big number, we want to keep big bits, which I guess just means that we parse the first number. This is 1. And what do we say we do here? We do times 10 plus the next digit, times 10 plus the next digit, until we like run out of space. I suspect that that's the wrong answer here. There's probably like some way to like think about this in base 2 directly, but I don't know what it is. So I'm going to do it this way. I guess you could also, if you parse out more bits than you need, you can truncate later. So you can like parse the mantissa into a U32 and then truncate to a U23 or something. And then figure it out from there. Do you really need the variable precision of floats for use case? Have you thought about using fixed point precision? No. I mean, probably not, right? I think fixed point precision is very likely okay as well. But I think in order to make that decision, I want to understand the float case a little better, right? I think that I can make a more informed decision if I go through this, and also it's just like a fun little puzzle, right? I think you're very likely correct that like ratio, like either doing like numerator, denominator, or fixed point or something, all of those are like great options, probably the best options. But in my brain, I was like, what happens here? And this is the problem I want to solve now. Even if it's not like, let's be clear, getting sidetracked here is a feature, not a bug. The background is more how did this come into my brain than why is it like worth doing, if that makes sense. Worth doing is like a completely orthogonal concept to whether or not we do it. Yeah, I think that this makes sense. So I guess when we parse the power of 10, we can extract first digit pause, because that logic is kind of in here. Not necessarily. Let's just parse that separately. I think that's easier for now. For now, we'll just do a second pass. I don't give a fuck, dude. You can't stop me. First digit pause. So we don't care about dot anymore? Or I guess we kind of want like a digit iterator that will automatically skip the dot. I guess that's kind of more reasonable. Reasonable is wrong, but like more conforms to the way my brain wants to work with these things. So let's do this. We have some next function that will return, a character. And this is going to be like self is a digit iter. He is going to store his position probably, as well as the string that he's looking at. And this is just going to be 0 off rip. So we're going to take in some string. And we're going to return like S is S, and pause is pause. Cool. 0, I mean, sorry. Then I guess if pause is greater than or equals S len, we return null, we're donezo. If then we probably do like this is probably like a while true in here because we're going to skip periods, right? So if we probably do like to defer here, self pause plus equals 1. If S at position is equal to a dot, we continue because we don't give a fuck. Otherwise we return S at self pause. Oh, that's easy. Wow, look at that. Look at us. Sure. Okay, so let's make a digit iterator here. On like 0, 0, 0, 1, 12.15 or something, right? Now the problem here is that we need this thing to be clamped to like the first digit, which makes it feel like we need like we probably here find the first digit position. Yeah. So we go like while isless s len, it's like if si is equal to is not equal to dot and not equal to 0, yes, we break. There we go. So if we punch this guy in, we're expecting to see 1, 2, 1, 5. That's what we're hoping to see. I think that that's good. 1, 2, 1, 5. That's the win condition here. 1, 2, 1, 5, baby. Let's fucking go. Which means we should just be able to be like, for each of these numbers, we initialize this thing with the sample, the thing we're trying to do, and we probably, I guess this is all gonna go in like mantissa is, you know, get mantissa from sample or something, right? And then we can have like get mantissa is gonna return u23, and then this is like s for string or sample, whatever the fuck you want to call it. Okay, and then we're gonna say like val is going to be, you know, the character value minus 0 in ASCII. And then what? We have like var ret. Ret plus equals val. And we probably do like ret times equals 10 here on each iteration, right? And then we say like if ret is greater than stud math max int of u23, break. And then we like shift this thing until it fits in a u23. I think. That sounds kind of right. Now, I forgot about the fact that there's an implicit 1 in here, which is fine because bit base 2, that's fine. Okay, cool. So here we need to find the first bit. Okay. And then we just want this first bit to be at 23. And we know that it's going to be bigger, right? Not necessarily. So I think that we just... So first bit is this. There's implicit first bit in mantissa. So that means that the first bit is actually the first non-zero bit minus 1? Right? Because this number, if we have like 10000, right? 000 count leading zeros would give us like 1 2 3 or 0 1 2 or 1 2 3 here, right? And then we actually want it to be 1 over. So first bit should be 4 here, which means count leading zeros should be higher, but we're subtracting count leading zeros, so minus 1 here. I think that makes sense. So we want this to be 23, right? So we're like, if first bit is less than 23, we're shifting to the left. And then we do like return ret amount like this. Else it's first bit minus 23. And we shift it right. That seems reasonable to me. That's what I would do here. That's what I would do if I was me in this exact scenario that I'm in. Perfect. Okay. Let's just kind of see what we get. I guess printing in binary makes sense here. Weirdly. Okay. 129 here is pissed. I guess we just intcast this here. Fuck it. Okay. Some more intcasts. Sprinkle those around. He's pissed because this is not working. Interesting. So this left shift here, can we run this in GDB? I wonder if this works. No. Maybe I have to do GDB args though. It does work. Nice. Okay, so we got shift amount here is 21. Oh, that would do it. Maybe? Ret is 4? Oh, because it's 1 extra. So we need to mask off the first bit. Yeah. First set bit is this. Right? We count leading zeros, subtract from 32. Now, we need to clear that bit as mantissa has implicit leading 1. So we need to do ret and equals the bitwise not of 1 shifted left to something. Which is going to be like, this will construct something that's like a bunch of 1s with a 0 hole where the bit is that we want to clear, right? And that bit is like, I guess it's first set bit. I think. We'll see. uh, before clear. And then after clear. And can we... I guess it's fine. He isn't like this. Unable to cast runtime value. Oh, this needs to be, my bad. This has got to be a U32 one for this shift to work. And then here we need to cast this guy. Okay, still angry. Before clear 100, after clear 100. So we did this wrong. -1? Was I off by 1? Before clear, after clear. Nice. Okay, so this clears it. And then first bit should be... First set bit -1 or something? Okay. Which he's still not going to be happy about. Oh, wait, it is. Wait, okay. Okay, maybe. Maybe we have some mantissas here. Who knows if they're right? I don't. Who fucking knows? But we can try constructing some floats out of these things now and see what happens. Mantissa. And then this is going to be, exponent needs to be, so if we have I8 0 is 0, I8 127 is equal to U8 127, and then it wraps around. So I8 -1 is U8 max. So can we convert this easily to the exponent? Is it like bit cast the integer, the I8 to a U8 plus 127 with a wrapping add? I think yes. So we'll call this like float exponent. We need to like rotate the numbers so that it's centered at 127. So it's literally just like 127 like this with a wrapping add on power. Okay. Okay. Parse float. Let's fucking see it, dude. There's like a chance that this works. Float exponent is power. I wonder if we have to like round down or something. Seems kind of reasonable. I guess we'll see. There's a good chance that this gets like that our guessed power of 2 ends up being wrong somehow. That seems pretty likely. That seems pretty likely, but I guess we'll see. Okay, 65123 parses 65123. 10 parsed is 10. 4 parsed is 4. Let's fucking go, baby. That's so fucking sick, dude. Okay, let's get rid of any prints in here that aren't just like us. In string parse this. Oops. Did we fucking do it? So let's get rid of those before clear, after clear. Come the fuck on, man. Okay. So now can we try doing some things that are like actually decimals? 1.23. 0.005. Okay. Now it's mad. Now it is mad. Because the power could be negative here. So this is supposed to be an I8 and then a bit cast. God damn it. Okay. Exponent U8 I8 is int from float floor of the power. Okay. Exponent U8 is a bit cast of that guy. Now we can do this. All right, does that work better? Okay, so this is wrong now? Interestingly. So decimals, it looks like I bet the power is wrong here. I bet you if we do, I bet you it's something like the floor. If this is like a seal here, I wonder if it like starts working. No. Interesting. Okay, so our decimal processing is wrong, and I guess we have to figure out why now, which is not obvious at all. Okay. So we need to basically, I guess, can we like log this as the number we got? Probably, right? So we can probably print out the mantissa as decimal. So we can kind of show this is like 1 point a number in decimal, and I think that does the same what we want. I think that gives us some valuable information. Can we just actually log just the fucking raw dog thing here? I feel like that's kind of what I want. Okay, so... Oh, we should new line. That's annoying. New line, please. All right. So... okay, so for like 100, let's make sure that this makes sense. So can we go to Python here? And I think this should be like 1 point this thing times 2 to the power of this minus 127, right? I think that's what we're trying to show. So it's like 1 point this times 2 to the power of 133 minus 127. No? Really? That's not what this is? What if we just go up? This is neither of those things. Interesting. That's surprising to me. I thought that that's what this was. And so the fact that it's not is a little confusing. Because very clearly this is like correct. So what am I missing here? Can we do like 10? Or like 1.0 times... Oh, yeah, 1.0 for the first one times 2 to the power of 129 minus 127. This one should be definitely just 4, right? That makes sense. So it's the mantissa representation that's probably a little fucked here, right? I do this guy and throw a 30 in here. This is no longer going to be 10. So this is not, while this is correct, using the decimal representation like this is not correct. Surprising. Okay, but we can kind of show this a different way, right? We can do 1. Oh. Because the 1. Oh no, it's, okay, we just can't do it this way. This should be, can we show the mantissa with that like extra bit set? So can we do like mantissa with leading 1 should be count leading zeros of the mantissa. We need to put it back in, right? So it's like count the leading zeros and then say like mantissa U24 is a mantissa. And then this is like num leading zeros. And we do want to do like 1 shifted left by like 24 minus num leading zeros. Probably 23 minus this. And then like mantissa U24 or equals that. So this should be mantissa U24. Does this help us in any way? Mantissa plus leading 1. Does this give us information that I want? Okay. So here I don't really feel like this helps me either, but we'll see. So we have like this mantissa times 2 to the power of, oh no, wait, hold on. This thing is unconditionally supposed to be the 24th bit. I'm a dumbass. We don't have to do any leading zeros here. It's an implicit 1 here. Yeah, so this is just like this. We put the leading 1 back in the most significant bit. Yeah, let's try that. Okay. So we have like on the value of 10, we have this guy times 2 to the power of, 130 minus 127, right? Which is fucked. The fuck am I doing, dude? Am I fucking high? We must be doing something fucking stupid. I just don't know what it is. I don't understand, like, how this value is right, but we can't figure out, like, what the fuck math it's doing. What the fuck am I missing? It's 1 dot mantissa times 2 to the power of exponent minus something. That's what I thought, but like I don't know why when I do that, it's not giving me the value I expected. I guess it's like 1 plus this value over 2 to the power of 23. I guess that's how you do the decimal component. See my comment, please. Did I miss it? The mantissa value is something like v2, v over 2 to the... Oh, you just got me. Yeah, we got... I did... Maybe I saw it by mistake. So then this is still giving me 3 and not 10? So what are we missing here? This guy gives me 0.25. Okay. So 1.25 times 2 to the power of 2, 3. Okay. So that seems right. Oh, because I didn't put the brackets around the plus. It's more like this. Okay, there we go. We fucking got there. We fucking got there. So for these, like, fucking broken-ass ones, we gotta figure out why these are wrong. Right? So now, at the very least, we can understand that, like, this over 2 to the power of 23 is 0.92. So that's where this is coming from, I guess? Right? Because the exponent is 0. That makes sense. So they're literally just, like, adding this thing. And so this should be, like, 1.23. And the question is like, what the fuck is happening there? So I guess that means that we want something like the value we're looking for is so we have like 0.23 is equal to x over 2 to the power of 23, which means that we multiply 0.23 times 2 to the power of 23. This is the number we're supposed to have. Right? Ish. Probably rounded, right? So we're supposed to have like this. And does this look like this number in some way if we look at it in binary? Maybe. Who knows? Let's see. Okay. Are these things related in some way? Interesting. So, like, it's like correct up to some amount and then losing its shit. Oh, I guess our mantissa parsing, is that wrong in some way? Like, here is the fact that we're always times equaling 10 wrong here? I wonder. Yeah, it could be something like that. Could be. Could be. Let's think about this. So, here at this point, what are we expecting to see? I don't really know. Got, you know, decimal value is this. I wonder if this is like reasonable in some way, shape, or form. That'd be before we do any of our like clearing and shit. This is probably supposed to be something that we can interpret. Right? Must be. Right? So like here, decimal value for in 4 is 4. 10, decimal value 10. 100, decimal value 100. Okay? 95123, decimal value 95123. 123, decimal value 123. Okay. 5, decimal value 5. So all of this decimal value that we're parsing out of this thing, it is doing what we expect. Now, I guess we're supposed to shift this whole thing left so that the top bit falls off. This is something about this is like confusing to me. So 123 is somehow supposed to turn into 0.23. I think. Because that's what we did, what we got. We saw like this value here that we're actually using. This divided by 2 to the power of 23 is like the decimal component of the value that we're seeing, right? So it means that like this guy somehow has to turn into 23, which is confusing. Because like when would decimal 123 ever turn into like 23? That doesn't sound right to me. It does not sound right to me. I'm confused. What is like the value that we're parsing? 1.23 is turning into exponent 0 here is maybe wrong. The fact that this is just looking at the data raw might be the problem. So like, how would we want to represent this number if we were doing it all from scratch? We were just trying to represent 123 as 2 to the power of something. We would want 2 to the power of like 6, right? And then like do like 123 over 2 to the power of 6 or something. Whoa. Whoa, 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 wait, that's the number. So there's a mismatch between the expectations of what we are expecting to parse, what exponent we think that we're using here, versus like the exponent we found. Right, so let's just say, so we need to add, oh no, wait, because this is 1.23, not 123. Sorry. But that does definitely give us a clue on like what the fuck is going on here, right? So we need to shift this thing right or something? Huh. Why are you returning Mantissa U23? Should it be U24? I think Mantissa is a U23. Mantissa is an implicit 1 in the 24th bit, 0.23 bits of shit in base 2. Oh my god. Okay, so this number totally makes sense if we parse this thing as 123, which we did. So then, what do we do to turn 123 into 1.23? It's like 123 gets divided by 100. Right? Yes. Which... So what the fuck are we doing? So 1.23, we get, this is like 10 to the power of 0, is like 1.23 times 10 to the power of 0, right? That's kind of how we parse this thing. So then we say, okay, 10 to the power of 0, that's like 2 to the power of 0, right? That's the equivalent power of 2 is 2 to the power of 0. And then I guess I wonder if we have to like do some sort of like division or something to get like from, because like we're doing some sort of division to get from like power of 10 to power of 2. There's some sort of linear relationship there. Surely we don't have to do something on the other side for that. Why does this work for fucking not big numbers but not small numbers? That's also confusing. Right? The fact that this works for these guys, maybe it's just because the exponent is small? Can we try like a really big number? Does it work for a really fucking big number? Like if we type in like 999,999,99 or something. No. No, it does not. Okay, so we've done something wrong. That makes more sense. That makes much more sense. So, what happened here? We have this guy over 2 to the power... Oopsies. This guy over 2 to the power 23 becomes 19209. Which feels wrong. I think the whole point of floating point numbers is you have more precision for big numbers and very small numbers but lose the normal range. At least that's what I remember. I think it's just more that like you only get the most significant bits. So you kind of get like good precision around like 2 to the something. Fuck. So it's interesting that like this thing worked for all of these guys, but not for this. I think solving the big number will be easier than the decimal numbers. And this will maybe just unlock the same fix. Okay, so what this number? This is like import math. This is like in the order of 2 to the 26. So 153 minus 127. So we got the right exponent here. That's what we got here. And so it's again the mantissa that's wrong. So what are we expecting to get here? The algebra is 1 plus n over 2 to the 23, right? Times 2 to the power of 26 is equal to this. This is the equation, right? Which means that we go like this over 2 to the power of 26. Take this out. Minus 1 to get this out. Times 2 to the power of 23. So let's just double check if we were to make a float out of this guy. We go the other way, right? So we go this over 2 to the power of 23. 1 plus this times all of this in brackets times 2 to the 26. Yeah, okay. So that's basically this number. It's, you know, a little bit off, but 1, 2, 3, 1, 2, 3, 1, 2. 1, 2, 3, 1, 2, 3, 1, 2. Yeah, this is basically that. Okay, so we were expecting this number. And instead we got this number. What the fuck did we do wrong? Are these two numbers related in some way? Right? That will give us a clue. You know, is this like a power of 2 off? No. But I guess we're actually looking for the one with the leading one. So let's do this plus 2 to the power of 23. Oh, that's a really good clue. So we're like doing something just fucking stupid. We're like looking this thing we're looking at this thing like it's in decimal, and that's like the wrong idea. So are these numbers related in some way? That might give us a clue. 1.25. What is like math log 210? 3.3. So it's not that. Dude, my poor dumbass fucking brain. My poor dumbass fucking brain. So where is this number fucking coming from? Because that's the correct answer. And this is like not related to the decimal number I'm seeing at all. Okay, can we do like what if we guessed the power wrong here, right? Let's just kind of throw these like 26, 27. Hello? Why can't I? Oh, unexpected indent. I see. Fucking Python. So like 27 or sorry, 27. Hello? What the fuck am I doing wrong here? This guy? 25 and 27. I don't understand why it's negative. But sure. So if I guess this number, if the power is off, that doesn't really change anything in a way that makes sense. The fact, okay, so what number are we actually getting? We're getting something if we say this plus this number times 2 to the 23 is this number, which is what we did the mantissa out of. And it's that's just like the wrong concept. The right concept is to get this somehow, which I don't understand how to get it. According to IEEE 754, just freeball. We're just kind of freeballing it first, and then we're going to compare with the right answer later. And again, I need to do this math again because I need to solidify this knowledge in my head. So this over 2 to the power of 23 is this value. Okay, makes sense. Some arbitrary thing it feels like. Then we add 1 to this, and we get 2.5 almost. And then we do all of this times 2 to the power of 26. Whoa, that's not right. I've lost my numbers. I've lost my numbers. I don't know which of these fucking things was right anymore, and it's melting my brain. It was this one. Is this the number we want? 1 plus this over 2 to the power of 23 times 2 to the power of 26. Unmatched. Bracketeer. Yes. Okay, so this is the right answer. This. And so I want to know what the fuck this number is. Okay. Approximately 1.5 is this whole thing, right? And so, like, where the fuck is that coming from? I mean, it's coming from the fact that 1.5 times 2 to the 26 is like the number that we're looking for. Dude, my poor stupid fucking brain. My poor stupid fucking brain. So is it because we're like we parse this number in decimal. And I guess we want like power of 10 here, surely, and power of 2 here, and these things are like related in some way. It must be something like that. Right? These two numbers together, they must convert this in some way. Right? So we have something that's like a times 10 to the power of b. We have a, this is like ret that we've just parsed, right? Times 10 to the power of p10 is equal to mantissa, kinda, times 2 to the power of p2. Right? So it looks like to me that we need to like multiply ret by power of 10 divide or times this ratio. So we have 10 to the p10 over 2 to the p2. Can we... Is there a way to calculate this without having to like expand them? It's gotta be, right? I feel like this is just... Have we already done this? Oopsies, I didn't mean to close that. So we have like 10. Hello? 10 to the power of A divided by 2 to the power of B. Is there like some sort of like simplification of this? I feel like there should be some sort of like trick here. But I don't know what. Okay, am I willing? Is it time to give up? Is it time? This is really close to change of base for logs. That's how I'm feeling, right? It feels so close. Right? Like if you have like... It's called the lookup table. Yeah, I guess you could lookup table this in some way. Okay, my problem is that I'm like short on time today. So I can't go over, which means that if we want like a satisfying resolution to this stream, we have to give up and look at the answer. It's the only way. So while I would like to keep going here and figure it out, I think that I've hit a wall. Or not, I haven't hit a wall, but we just don't have time. So I suspect my suspected answer is that we're supposed to do some sort of conversion of the base 10 number that we find. We have to convert that into a base 2 number that is related to the equivalent power somehow. And I'm not sure. So can we look up? Maybe we can look at the Zig implementation and see if they have any help for us. Format, parse, float. So what do? They parse the negative. They parse the number from... They parse the number onwards. So parse partial number of this guy. They have like special hex handling, but then they have a float stream. Okay, so they parse partial number base. They're trying to parse a base 10 number where they're saying the maximum number of digits is, whoa. Manticity is mantissa type. So U64 here. So they're saying we have 16 bytes, or 16. Does 123 over 100 equals 123 over 2 to the power of log 2 100 help? Maybe. I'm not sure. I don't have no time. So they're saying we have 16 digits that we can parse with here. And so I assume they just like parse the digits here. And then what? So they find the number in base 10. Then they're handling like too many digits and shit. Holy shit, there's a lot of stuff. Then they're like, okay, we had too many digits. But all of this is still base 10. I think. Right? They're calling partial number base with base 10. And so this returns a partial number, which gives us this gives us exponent and mantissa out of this guy. And then what do they do with this partial number result? They just return the number. Sure. And then parse number is n here. And then they have to do a conversion, which I assume is like a base 10 number here. Yeah. So fast pow 10, upper bound for tables, blah, blah, blah. But it looks like this is doing that like power of 10 thing that we wanted to do. Yeah, so they divide by power of 10 here. Or multiply depending on which side it's on. Oh, and I see. There's like this is the fast path, which is we didn't do because we're like, we might not fit this thing in an i64 or whatever. I think. Oh, then they like shift this and then do some other shit. Okay, so it's like not even close. Not even close to what we did. Can we look up like on Wikipedia? Parse float or something? Is there like, I want to like see like someone parsing this from a string. Converting decimal to binary 32. Here we go. So what do? Consider 0.375, the fractional part of this thing. To convert it into a binary fraction, multiply the fraction by 2, take the integer part, and repeat with the new fraction of 2. So they go, oh, interesting. So they multiply this until they find that it grows. And then this is like above. So this is like 375. It's like they multiply it by 2 twice. So that's going to be 0.01 probably. So they're going to compose this of like 0.125 plus something else. I see. So then they split this thing into the fractional part and the other part. Ah. So that's where we were getting it wrong probably. So cuz converting this thing, we were converting into the the top half correctly, but the bottom half we were not doing correctly. So then they get, whoa, what's going on here? So then when they have that, they have then they just shift it until it's the right power. I guess. Hold on, let's think about this. So they take the lower half this becomes 0.001. Yeah, I see. So then they shift everything left until basically this thing fits in a U24. And then that becomes the exponent mantissa. Neat. Okay, I think I understand. So where we were going like heavily wrong was processing the stuff to the right of the decimal. Right, we just did that completely wrong. But this doesn't explain exactly why our like 9999 was wrong. Right, I would think that that's still right. Oh, because we were doing like they're not doing that like guess power of 10 shit that we were doing at all. We thought that that made sense, but they just I mean, this feels like it doesn't really answer the question to me, right? Because this kind of requires your number to fit in like wherever you're doing the arithmetic, which was the problem we were trying to avoid. I'm not really convinced that this works. Because what if your number's just big as fuck? Right? Right? So, like, I don't think that this is the right answer. Parse float implementation. Maybe this guy's an answer for us. Divide the integer part by 2, becomes bit and binary number we were building. Quotient replaces the integer part, and we repeat until the integer part is 0. If we have a decimal number, we can easily convert to binary by dividing the integer part by 2. The remainder becomes a bit in binary, and the quotient replaces the initial part, blah, blah, blah. So for example, starting with 13, divide by 2 to get 6, right? Because 6 times 2 is 12. Remainder of 1, then we divide 6, blah, 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 blah. So then the bits we produce were this. Oh, so you can kind of buffer the binary string somewhere. I guess you can exceed the number of bits you can fit in i64 if you just buffer the bits this way, right? So instead of trying to like pack everything into one integer and then do math on the integer, you can have like a bit sequence that could be as long as you fucking want, and then you can you can like process up until you hit some amount of bits, and then keep processing until you find the power without having to write anything down. Is probably where this is going to go. Okay, so we had the wrong approach, I think. It makes sense. It might be interesting to take another run at this in the future, but again, unfortunately, we ran out of time. So, at the very least, we learned that what we would do is not correct. And I think that's a good enough piece of learning for today. Apologies that it's not a more satisfying end. I would have loved to get something that was worked, but time is not on our side. So, thanks for watching, guys. I hope you had fun. I had fun. If you liked what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. This is kind of like a one-off stream. As of, recently we've been working mostly on a website to like track what food I've been eating, so that I can like be like, am I eating 4 days of food per day, 1 day of food per day, quarter of a day per day? Who fucking knows? Maybe we can use that information to like create shopping lists and stuff like that. There's a lot of other stuff on YouTube. The other project that we've been working on is making a controller from scratch. So, we were 3D printing this guy, trying to write some firmware, trying to make a PCB, and all that shit. So we'll be back on that soon. But we're kind of doing the website thing first. If you want to keep up with what we're working on, there's a YouTube link in the Twitch description where the main segments of streams go up. All you saw today was what we would consider main segment, which is like generally like a thing that can be titled and thumbnailed on YouTube. And then there's kind of like other stuff that we, sometimes we do research, sometimes we do unit testing, sometimes we do cleanup, and that stuff it's like harder to package in a way that YouTube would accept, but is still something that I would like to like document and have up for people to watch if they want to. So the other segments of the stream, they go under the Patreon, YouTube members, or Twitch VODs, which gives people who want to make the stream continue. It gives them something to get if they give me some money. So this stream will end when I run out of money, right? So every dollar I make while doing this extends the lifetime by some amount. So if you would like to see the stream continue, please consider supporting, but obviously no pressure. I think that's all the plugging we gotta do. That's our end wrap up. YouTube, peace out, and Twitch, let's find someone to raid.